Let's take a look at an example where you could use Lamport clocks to actually do something for real. I'm just thinking, the example is not too realistic, but if you ask me, have Lamport clocks been used for situations like this, then the answer is yes. But this is just a very good example to see what you could do with these Lamport clocks. Okay, what I'm assuming is the following. I have a system, a distributed system, with two replicated databases. And these databases, they just hold accounts from people. And there will be two concurrent operations. One operation is that you have a process that adds $100 to an account, which was initially $1,000. And the concurrent operation is that it increments an account with 1%. And now you can easily see that if you add and then add $100 and then increase the account by 1%, then the end result will be higher than first incrementing it by means of 1% and then adding $100. The difference is $1. Okay? Does everybody see that? So what is important in this situation is that if these two databases are replicas of each other, then the ordering of the events should take place in the same order. Should be the same at both sides. So what we need to accomplish is that I don't care which order, namely the add above the interest increase or the other way around, as long as the order is the same at both sides. And we're going to establish that by means of Lamport clocks. Logical clocks. Oh, by the way, I'll be a bit sloppy in my terminology. I'll talk about Lamport clocks and logical clocks and perhaps counters. The context should be enough to distinguish what I'm talking about. Okay. So pay attention because it's not entirely trivial. So what happens? First of all, I'm assuming that all the processes behave according to the scheme I just explained. That means that you timestamp messages according to your local counter, you send things up, you send things across the network, and then when you receive something, you adjust your counter according to the rules I just explained. So if you're too slow, you fast forward in time, and then you assign the right timestamp to the message. Okay? And again, the databases in these cases form actually the application. And it's the middleware that assigns these timestamps and keeps all kinds of administration around these messages. That's indeed in the middleware. And at a certain point, you can hand off, or hand out, I should say, the operation to your application, which really means, yes, you can now execute it on your database. Okay? So I have a bunch of these processes. In my example, I had two. Process PI sends a timestamp message to all the others. The message itself is put in a local queue. This is what happens in the middleware. Okay? Any incoming message at a process PJ is queued in its local queue according to the timestamp and acknowledged to every other process. So your message comes in, you timestamp it, and now you put it in the queue. So unlike Lamport, before handing it off to the application, you make sure that it gets a position in the queue. As soon as it's at the head of the queue, and you're certain that you can actually hand it off, that's when you actually pass it on to the application. So that's the difference with the core explanation I just gave of the Lamport system. So when can you pass a message to the database? If that message is at the head of your queue. So watch this, look at the indices. PJ passes a message I that it has in its queue to its application, being the database. When that message is at the head of the queue, and this is a crucial one, for every process that is participating in this algorithm, there's a message K in that queue with a larger timestamp. I'm assuming that the communication is reliable and FIFO ordered. FIFO ordered means that if I send two messages in a row, my messages will be received at the other side in the order that I sent them. No, I don't think I'm blocking anybody. Well, I'm blocking myself until a certain point. And I'm really not blocking, I'm waiting until I can pass a message to that application. Am I waiting on other... Why do you say that? Why do you say... I have to repeat. Why do you say that I'm waiting for other processes? All the processes have to be in the same state to process all the messages. That's not entirely true. I think you're very close to the answer, but I'm not sure. Can you mention a characteristic feature of these queues? Yes?
Do we need one particular?
Yeah, so let me try to summarize this one. Do you need a priority queue? The answer is absolutely yes. But that's not the crucial observation. There's something else going on. Yes?
Because time is synchronized between all the nodes. Because of the counters, all the messages are put in a queue based on the timestamp. So all the nodes have the same ordering of all the messages in the queue.
Thank you very, very much. Thank you very much. So here's a crucial observation. Very good. Here's the crucial observation. The queues are alike. They're not necessarily exactly the same because you don't know exactly which messages have already been arrived or have arrived at messages, at queues. But let's assume that you do not forward any messages to your application, just as a thought, okay? And that at a certain moment, everybody says, okay, I'm fed up with it, I'm not going to send any requests. What will happen, under the assumption that communication is reliable and FIFO ordered, you will actually see exactly the same queues at every process. For exactly the reason that you just mentioned, we will have a globally consistent timestamping of messages, requests that are now in the queue, right? So everybody will have these messages with a consistent timestamping. Consistent in a way that the ordering is completely preserved. Yes, they will have exactly the same queues. Very good. That's a crucial observation. Okay. So that means that if everybody, under this ideal scheme that, hey, we don't pass anything on to the database, okay, and everybody at a certain point just stops sending requests, you will see that everybody has exactly the same queue. Okay, that's fine. Will you please pass on your first message? Because everybody will pass on the same first message, which is the same request for an operation on the database. And then number 2, and then number 3. Everybody will do exactly the same thing. Okay. Why this condition? What does this condition say? The second condition. I will pass a message at the head of my queue to the database as soon as I find that there is no other message in that queue. No, wrong, sorry. As soon as I found a message from every other process in the system in my queue. So we can revert this. Why can I not send a message to my database when it's already at the head of the queue? And I just ignore condition number 2. Yes?
Because every time?
In a minute, I will ask whether it's necessary to send acknowledgements. So there's something else going on. So I'm going to revert the question. Suppose that I ignore condition 2, and I just take a look at the message that is at the head of my queue, and I just, forward it to my application. What could go wrong? So what can happen is that a message may arrive later with a lower timestamp. Okay? No, that's okay. Can I just keep a track of the last message, basically, that I sent? No, that's not going to fly. There's something else going on. And it's very easy to see it like this. Let's just start the system. So I send a request for doing an update. my message gets at the head of the queue. Okay? Now the problem is, I don't know if there is another process out there who's also requesting an update of the database. I just don't know. Who's just timestamped its request with a lower timestamp than mine, which may happen. I would, maybe I had some internal events, and I just timestamped it with 10. You did not have a single internal event, and you timestamped your request with 0. Regardless, our process identifiers, you win. And to make it even more confusing, this is very important, I timestamped it with 10. Okay? Now you are really, really late. I did this at 3 o'clock, but your counter was still 0 at 4 o'clock. And you timestamped your request with timestamp 0. You're first. Got it? And that's just what you said as well. This is the extreme case. I am not permitted, for the sake of consistency, to hand out my request to the database because there may be a message floating out there in the system, a request, an update request, which will get a lower timestamp than mine. You go first. That's the whole trick. So I wait until I've received a request from everybody, a message from everyone. These messages got ordered. If you now send me a message with a lower timestamp than the message that you already sent, you're violating this condition. Okay? So if I use that condition and I get a message from you with timestamp 5, I know for sure that I'm not going to get a message from you timestamp 4. Because that would violate this condition. So I'm safe. 5 is now your oldest message. And I can check that message against my message, which may have a timestamp that is higher than 5 or lower than 5. That really doesn't matter. I know where to order it relative to your message. And then I can do this for all messages from all, for messages from all other processes, and then I have a complete and consistent view, and I know that my neighbors have exactly the same view. Whoops-ah, we start throwing messages to our applications. Yes?
How are you going to handle a crash process?
How am I going to?
Handle a crash process.
I'm not. How am I going to handle a crash process? I'm not. Thank you for this question. So, what is the problem with this scheme? I remember the words that I said, I think, during one of the first classes. I'm one of those teachers of distributed systems that will tell you that in many cases the best solution for a distributed algorithm is a centralized one. Here you have an example. Because if you have one crashing process among 25 processes participating in this algorithm, the whole system comes to a grinding halt. What I've just done is I have explained you a really nifty algorithm that now has just replaced, if we would take an alternative, namely a centralized solution, that has just replaced a single point of failure with 25 points of failure. Is that going to make you happy? Not me. Yes?
The message you have sent.
But that doesn't, okay, so I'm trying to see if I understand your question. Actually, I'm trying to see where this question comes from, which is often more important than the answer. What you're saying is that, let me try to see if I understand your question. What you're saying is that if I know my own counter value,
And your second message.
no, I cannot, No. I said something else. I said I cannot remove the message from the head of the queue and pass it on to the application if I did not receive a message from every other process, and watch this, which has now necessarily, none of these messages are at the head of the queue. Why are we waiting? Well, you just gave an answer to that question just a minute ago. Because I don't know, not to the last one. I just don't know, irrespective of my counter value, if there is a message that was sent with a lower timestamp than mine. Now I see where your question comes from. Okay. So this is what you do as a teacher. Now, this is an interesting thing. I'm often not interested in the answer. I'm answering, where did the question come from? Your question came from the following assumption. When I order the messages in a queue, I do that by the timestamp they got when they were sent. And you were assuming that they were timestamped according to the reception time. This is a very good question. I never realized, no, this is very good. I never realized that this confusion could start. So this is what I do, and I hope I got this right. I timestamp it, okay? It sends it, I timestamp and I put it in my queue. And what I should have made it more explicit, the ordering of messages in the queue is according to their sending timestamp. That's where your confusion comes from. I hope. Am I correct?
Make a process 1, process 2, process 3.
You can do that now.
Yes, I will do that.
You do that now. But you see, so this is important. They get ordered according to their sending timestamp, which is still consistent. Now coming back, where are you? You used to be over there. Where? Oh, no, he's gone. Okay. This was the question about concurrency. When is it necessary? Okay. Here you see, I'm looking like hell, but I can't find you. Okay. So here you now have the situation that if you do indeed have two concurrent operations, I was sitting over there actually. If you have two concurrent operations, you will now have to listen to the recording. If you have two concurrent operations, they actually could get the same timestamp on when they were sent, right? And I still have to make the decision of who goes first. That's when I need the process IDs to do the right ordering in this queue. Got it? Okay. Very good, actually. Now, go ahead. You're becoming famous, you know.
So when, okay, I wait, let's say that there is another message coming with a timestamp lower than mine.
Yes.
Then I will change the head of the queue actually to that one.
Yes.
Okay.
If you got it, very good. Under the assumption that the timestamp of the message in the head of the queue is higher than the timestamp of the message you just received. Very good. You understood it. And to be clear, thank you very much for being so persistent in your questioning, because I'm quite sure that half of the people in this room could have asked exactly the same questions. Hooray for you. I'm dead serious about this. Okay, now let's see if you can then, or anybody else can answer the following questions. Do I need to send acknowledgements? Yes.
Waiting for a message from every node, then no.
Exactly. If I'm waiting for messages from every other node, and I know that they're going to send them, I don't need to send acknowledgements. Exactly. Because I'm not interested in the acknowledgements, I'm just interested in their timestamps. That's the whole thing.
That's because for constraint number 2, you're practically polling for the acknowledgement, right?
Yes, exactly. I'm basically calling for acknowledgements. The only thing I'm really interested in is the consistent timestamping and knowing that there's not going to be another message floating around that's going to overtake the message that is currently in the head of my queue. Very good. I think you guys understood this. Okay. Here we go.
How do you make sure this system doesn't stop when a node doesn't send a message because it doesn't have anything to send?
You don't. Oh, if it doesn't have anything to say, if you're up and running and you don't have anything to say, you're not playing by this deal, by this game, because then you have to send an acknowledgement. Okay? Otherwise, it will come to a grinding halt. And, okay, and then how do you actually use these systems in practice? Well, no matter what, processes will, if they have nothing to say, even if there's really nothing going on, will send alive messages. I'm here. Just to make sure that everybody is aware of what's going on. In practice, you see so many messages being passed around because these schemes are basically used for implementing fault-tolerant systems. That means that the process groups are fairly small, let's say at most a few tens, and in practice even just 3 or 5 or something like that. So you still see enough messages being passed around to circumvent all the nasty problems. But you do have to take them into account. Yes?
In this scheme, every node has to send an equal amount of messages.
Yes. Every node has to send an equal amount of messages. Be they messages with content, like updates, or acknowledgements. Yes. Basically it boils down to, if I send something, you have to send something back. I don't care what, as long as you send something back. Okay?
So we actually need those calls.
What?
So we actually need the acknowledgement to keep the node constant.
Yes. So what I said is, do you really need the acknowledgements? And the answer was no, if you always send updates. And the answer is yes, if you don't always send updates. But you need messages. But they don't have to be acknowledgements, because I'm only interested in timestamps. Okay? Okay, what I'm going to do, because this is so tricky, I'll start with vector clocks to plant a seed in your brains. And then I'll go through a couple of slides, and what I'd like you to do is to go over these slides as preparation for tomorrow. And then I'll go back to the slides. This is nasty stuff. And I personally have always found this to be nasty stuff. So like I said, this is one of the places in the book where you say, well, did he really understand what was going on? Of course I will say yes, but no real deep understanding. There's a lot of stuff over here. And if you are now asking yourself, if he's going to talk about vector clocks, are there also something like matrix clocks? Yes. They're even worse. But I want to get to the crux, and the real nasty slide is this one. Okay? So let's just probably discuss only these 2 slides and come back to them tomorrow. It's important. Now, one very crucial observation, and I've asked this a couple of times during exams, is that Lamport will provide you a consistent timestamping, but it will not say anything about causality. So if you have this relationship, namely the timestamp associated with the event is less than the timestamp associated with another event, this does not mean that that B causally was caused by A. Okay? And don't get me on the semantics right now. This is very important. I'm capturing everything at the middleware layer, because there's a big debate going on whether the middleware whether the middleware should even be concerned about this. Okay? So this is an important observation. If you take 2 events, you see the timestamps, you cannot conclude that if this timestamp was lower than this one, that A caused B. Or that there's even a causal relationship between the 2. And here you see this is a very simple example. You see M1 and M2, okay? M1 was sent over here, received at 16. M2 was sent at 20 and received at 24. You cannot say anything about any relationship between these 2. In fact, these are 2 completely independent messages. Nevertheless, if you take a look at timestamping, you may want to say, hey, what is it? M2 was sent because M1 was sent first. Or in this case, was even sent after the receipt of M1 by P2. So there must be something going on. All wrong conclusions. Okay? So what I want to do is I want to capture, and I'll be a bit more precise, potentially causal relationships. And what I do is I keep track of what's going on in the entire system. Every process maintains an array of clocks where VCIJ means the number of events that process PI knows have taken place at process PJ. Okay? And I have to make one important assumption, and hope it's on this slide. Here it is. Do I do this here? Sorry about that. Get to that in just a minute. Keep in the back of your mind that we're now only going to timestamp when we send things. We're no longer going to timestamp things when we receive them. Okay? Because I'm trying to establish something else. I want to establish this capturing of causality. When PI sends a message, it sends the entire, first it adds 1 to its local clock. Hey, I'm sending a message. Okay, that's consistent with what we did with Lamport. And it sends the entire vector along with M. And now we have a vector timestamp. And basically what it's doing, I'm telling you this is what I knew about the other processes when I was sending this message. That's basically what's in this timestamp. Okay? And now we had a brief discussion on scalability. Here you see a scalability problem, because if you have many, many processes, you have a huge vector to send. And actually there has been research on how you can compress these senders or send less information. So when M actually arrives, the recipient, PJ perhaps, would actually now know PI's timestamp at the moment it was sent. Okay? When a process PJ delivers a message M that it received from PI with a vector timestamp, let's first follow the Lamport rules. You update VCJK to the maximum of what we had. This is exactly what we did with Lamport. Okay, just this single entry, and you increment your own entry by 1. I'm going to drop this one in just a minute. But that's for capturing causality. But so far it's still Lamport, but now I do this on all vector entries. What does VCIKJ is K mean in terms of messages sent and received? And just to keep it simple, I'm not going to timestamp any internal events internal to a process. And I'll keep it even simpler. Let's drop this one as well, number 2. So I only timestamp messages when they're sent. What does VCIJ is K now mean? Yes?
I think it means that process I thinks that process J has sent K messages.
Say this again? I think you're right.
Process I thinks that process J has sent K messages.
Yes. So you see how important this information is? Process I thinks yes. I'm trying, I have to make sure that this is correct. Process I knows, not even thinks, knows that process J has sent K messages.
It doesn't have to be true. Because
Oh.
J might have sent some messages that didn't involve I at all. So you wouldn't know if the actual counter matches his local counter for us.
Oh, sorry, that's why you, okay. Okay, absolutely correct. It doesn't know for sure. Well, it knows for sure that it has at least sent K messages. Okay, so that's the knowledge it has. Okay.
Received message from J. Isn't that right?
It?
Well, when you send the vector, you basically synchronize with the node that you receive the vector from. So from that
Almost. Don't. Not yet. This is on the next slide. Okay. But the point I wanted to get is you're counting sent messages. Okay? And the crux of the matter will be that when I send a message and I timestamp it with the knowledge that I had about messages that were sent, I'm telling somebody, I sent this message when I knew that these other guys had sent so many messages. And now you can see that you can, by cleverly counting things, I can say, I sent this message after having seen so many messages from each other process. And if I now assume that messaging abides by FIFO ordering, I'm telling you, I sent this message after I had seen so many messages from any other process. And now I have a causal relationship.
Does that mean that say I'm process I and I'm process J, and I think he's sent 5 messages, that when I send you or him a message, I say, I send message number 6?
Just a minute.
Or do I, okay.
Hold it. So I'll wrap this up, and then I'll come back to this tomorrow again, okay? But you're very close. So now, having this, we can actually ensure that a message is delivered only if all causally preceding messages have already been delivered. And I should say potentially causally delivering. I'll come back to potential, well, you know the answer to that one, but I'll come to that in just a minute. So I make this small adjustment now. PI increments VCII only when sending a message. And PJ adjusts VCJ when receiving a message. That is, effectively does not change any, only changes the maximum things, but not its own VCJJ. Okay? And it postpones delivery of a message until these 2 conditions hold. Now let's see if you can translate these conditions. The first one is relatively easy. So I receive a message that is timestamped with this vector. And I take a look, I'm process PJ. Okay, I'm the recipient. And I see this message, and it has this. What does that say? Yes? Yes, exactly. That's a very accurate one. This one says, I have received so many messages from I. This must be the next one.
J doesn't have to have received all of the messages, right? These messages could be sent to other processes.
Of course.
Okay.
That doesn't matter. But the messages that I received from I, okay, I've received all of them, and this is the next one. Oh, this is, let's assume multicast. Everybody's sending messages to all other processes. Okay. Whoops, very good. Okay, so this is also the message that I sent, that I received from the other one. What does this one say? What's the second condition?
Is this to say that you should receive a message from everyone?
No. But you're getting close. Yes?
Says that all the other processes don't have any messages left to send that I don't know about?
Say this again?
It says that there are no messages from other processes that I don't know about.
A bit more. You're virtually there.
Could it be a delayed message?
No. I think you can finish it. If I'll finish it for you, then you'll say, oh yes, of course.
The messages I knows about.
Getting very close. You know what it is? I have seen all the messages that the sender had seen when it sent message M. And you were almost there. And you said, I do not have to expect any other messages. But that's true, by the way. But it's just, you can sharpen this a bit saying, I have seen all the messages that the sender had seen when it sent this message. I have exactly the same information that the sender has when it sent this message. Good. That means that I can now send off this message to my application. All the knowledge is now there. Any potentially causality, I have already seen that as well. And I'm expressing potential causality in terms of messages sent and received.
So you don't have to wait for all the other messages in the queue or for the plus, so for the next one.
Well, the only thing that you have to make sure is that these two conditions are met. This could be a long waiting. Okay, first, this is an easy one. This is the next message that I would expect. And this could be, I have to wait until I've seen all the messages that this guy had seen when it sent message M. Otherwise, I'm passing stuff onto my application based on potentially impartial knowledge. Because I haven't received everything that this guy had received when it sent the message. That's what is in the second condition. And of course, I'm assuming that if you've seen that stuff, you've passed it on to your application. So the translation could also be, I have passed everything that my application needs to know to understand this message that was sent when that part of the application sent that message based on all the stuff that it had seen. My application has seen exactly the same as that application. That's the main thing. Let's come back to this tomorrow afternoon, sorry.